Here we'll look at symmetry of solid state. Before that, we were looking at molecules that were relatively free, being in gas or in liquid. But when we are coming to solid, atoms are closely connected to each other, and they have additional symmetry that is coming from the fact that we all exist in three-dimensional space. You may want to look at all this material. The highest symmetry we have is cubic, when all three dimensions are exactly equivalent, like they are in empty space. And next step we'll do is simply look at how spheres can be arranged in three-dimensional space. The most primitive way to arrange them is a simple cubic unit cell. So we have a cube, and at each of vertices we have a sphere. It's very simple way. Alternatively, again with cubic, you may have one sphere in the center and same way 8 others arranged around it. This is so-called body-centered cubic unit cell. Next option is face center. We have spheres at each side of the cube, and then we have spheres at each of vertices. So face center cubic cell. There is no other option when we consider cubic packing. This last face center cubic cell is closely connected to a problem of closest possible packing of spherical atoms or any kind of spheres. Close packing principle is coming from ancient philosophical statement that nature hates emptiness. This statement is known for more than 2000 years and was repeated numerous times by different philosophers. Very practical problem was how to pack cannonball so they can be stored, occupying as little space as it is possible. The problem was theoretically solved by Carl Gauss, same Carl Gauss of Gaussian, saying that face-centric cubic cell is the closest possible arrangement where empty space is the smallest. Occupied space is 0.74. It's of course infinitely precise number, and you cannot go beyond that point. Now there are two alternative packings. We'll look at them in detail. So when you pack as close as is possible in two-dimensional space, so in plane, you are packing as triangles in this fashion. Now, when you do next layer of cannonballs or any kind of balls, you are putting one new above 3. So you have the second layer in this way, it's black. Next, for third layer, you have two options. One is to put next layer above the first, again above 3, or you can put third layer above the void between 2. In this case, you are getting not hexagonal, this is hexagon, but cubic face center cell. So again, looking at it, first layer like this, it has hexagonal arrangement, so triangle, triangle, triangle. Second layer fits over alternate holes in the first layer. You cannot put at each hole because it will be too close, so you're leaving some of them empty. So that's how you arrange the second layer. Now you have options where to put the third layer. If you are putting them above the empty places, the voids of the first, you'll get cubic close packed. If instead you are putting next layer above the first layer exactly, you'll have hexagonal close pack. Again, packing will be exactly identical. The empty space will be exactly identical, but the motif is different. You are putting or at one or at another position. You have two choices for the third. Let's look at how we put first layers. Triangle, triangle, next layer of triangles. Now the second layer. So, what we see in reality. Simple cubic packing offers us very small number for total occupancy. Only around 1/2 of space is occupied. This is why we never see this packing in nature. There are some data, but that's tricky and questionable. Body-centered cubic gives occupancy that is very close to close packed hexagonal and cubic close packed. So this possible case, coordination numbers in body centered is 8, in hexagonal and in cubic close packed coordination number is 12. So the atom has 8 neighbors and 12 neighbors. Body centered happens in some cases. It's a first group and some second group metals, and there are examples among transition metals. Face center cubic is very common, as well as hexagonal close packing is very common among simple elements. But in reality we have different packings that they are they are not the best. The simplest possible packing of atoms or spheres is trigonal. What does it mean? You have any ambient angle between two directions and any ambient distances here, distance between atoms in this row and in this is different. Now, you may have this angle being 90 degrees. Next, you may have arrangement where there is one atom in the center, so it's more metric. Next, you may have hexagonal arrangement and you may have tetragonal arrangement. This is in two-dimensional space. In three-dimensional space, this results in so-called triclinic cell, the least symmetry. A, B, and C all are different, and angles between them all are different. This most general case. Next case is monoclinic, when you have two of angles being 90 degrees, and the third is not 120. Next case is hexagonal, and it's close related trigonal, where you have two distances A and B equal to each other, two angles being 90 degrees, and one is 120. Next case is different, orthorhombic. In case of orthorhombic, all angles are exactly right angles, 90 degrees. It can be primitive, it can be face-centered, and it can be body-centered as well. Even more symmetric is tetragonal, when two of sides are identical and all angles are 90. And the highest symmetry is cubic, when all A, B, and C are identical and all angles are 90. These 14 types of cell describe whatever is possible in nature to make solid state with periodicity. So usual crystalline solid state. We do not have any other options. It can be theoretically proven. And such lattices, such cells, we name Bravais cells. You may want to look at it in more detail. It's almost infinitive material. It's a profession studying packings of atoms and molecules in solid state. We'll stop at this for sake of 360